All right, ladies and gentlemen, class recording has started. So, this unit, we have been dealing with our atomic model, right? The picture of an atom. And these pictures up on the board right here were on the back of your outline yesterday. So if you want to pull that out real quick, you can, but we're just going to talk about them up here. If you don't want to pull out your outline from yesterday, that's cool too, okay? So this gives us a progression of what our atomic model looks like, right? Our model being a representation of something that is too big or too small or too complex for us to really observe in person. So, the models start up at the top with Dalton's model, and we talked about this a couple of times now, right? What does Dalton's model of an atom look like? It's a sphere, solid sphere. Why? It's indestructible. There's nothing smaller than an atom, according to Dalton's theory, right? So this is what Dalton's theory, this is what he, based on that experimental evidence, came up with in order to explain that and explain this idea of an atom. And you can see here these years that are on this timeline. They're approximate, so we're in the ballpark-ish, right? So early 1800s. Then next, J.J. Thomson. First, J.J. Thomson does which experiment? Cathode ray tube experiment. And what do we get out of the cathode ray tube experiment? Electrons, right? And so we have to change our model. Now our solid sphere has some detail inside of it. Specifically, those isolated negative charges, right? The blue circles, which we sort of likened to like chocolate chips in a chocolate chip cookie, right? Where the negative charge is contained in these specific pieces, but then the positive charge is just kind of like the rest of the cookie that makes up, the cookie, just sort of there. Okay. All right. Next, Rutherford. What experiment? Gold foil, right? Gold foil experiment gives us what? The nucleus, right? That's right there. The nucleus. Yeah, so we take all that positive charge and we condense it down into a very small, dense center space where all of the positive charge of that atom is and most of the mass of the atom. Okay? Good? All right. Over the last couple of days, we've talked about the Bohr model and then Schrodinger's model, right? So, what's the gist of the Bohr model? For what? Energy levels for what? Electrons, right? Bohr says that these electrons exist in these very defined shells or orbits around the nucleus. He calls energy levels. Joe, what determines what energy level an electron goes into? What determines what energy level that an electron goes into? Unicorns. Good. Well done. Glad we paid good attention the past couple of days. So, what determines how far or close it is from the nucleus? The shells. What one word is plenty. Energy. You said unicorns. So, energy is what defines which shell it goes into, or which orbit it goes into. So,
I said energy.
Gotcha. But then you listened to Hassan and said unicorns instead. I did not. So, no, I didn't hear that. So.
Right before that, I said energy.
Sorry, I did not hear that. Right? We should go back. So, all right. Energy determines what shell these electrons go into, right? Are the electrons able to move between those shells? Yes. What do they have to do in order to move from one shell to the next shell? Either gain energy or lose energy, depending on whether we're going up or we're coming down, right? All right. What's wrong with Bohr's model? Worked pretty well for hydrogen, but everything else maybe not so much, right? What do we learn later on that sort of explains why Bohr's model doesn't work very well? Okay, now what are you going to say? Okay, electrons repel each other. That plays a role. That gets us into the no-defined orbits, right? We also figure out this idea that no defined orbit thing, right? Yeah, so we learned that. A lot of that comes about because of the uncertainty principle. Okay, do we remember uncertainty principle from yesterday? Okay. What does uncertainty principle tell us? Or speed, right? We can't find the exact location. I should have said and speed. We can know one or the other, but we can't know both. Okay? That being said, say again? Like Usain Bolt when he's running that 200-meter race, because that's his better race, right? Okay. All right. So that leads us to Schrodinger's model of the atom that shows up down at the bottom. What is the gist of Schrodinger's model?
Electron cloud.
Okay, electron cloud model. Yes, what does that mean? So, okay. Probability plays a big role here, right? Okay. So, unlike Bohr's model, do we know where electrons are? Not definitively. What do we know, though? There are high locations of high probability. Bella, you were getting there, Bella. You were getting there, right? There are locations of high probability, but the possibility exists that electrons could be anywhere surrounding that nucleus. Like on the moon, right? We talked about that yesterday. Is it possible?
Yes.
Yes. Is it probable? No. Right? Okay.
How unlikely?
Very. Very. Think about.
How?
Like, very, very. All right. Before we move on to the next section, okay, the next part, let's talk about this picture down at the bottom, picture of Schrodinger's electron cloud model of the atom, okay? Because this can be kind of confusing, so I need you to understand it before we move on, okay? All these black dots, okay? Those black dots are not electrons, okay? Those black dots are places where electrons have been in the past. Okay? Okay. How do we know where an electron has been in the past? Could take a picture, yes. Although it's kind of hard to actually take a picture of an atom though, right? Okay. What mark does it leave? What kind of energy?
Thermal. Light.
Remember we talked about these light bulbs?
Feeling.
Yes? What happens?
Mercury energy.
What happens in these light bulbs that allows it to give off light?
Releases energy.
What kind of energy goes into it? Electrical energy goes into it, and that causes the electrons in these atoms to do what? Gain potential energy. They jump up. But then, do they like being in those higher energy levels? Fall back down. What do they do when they fall back down? They release energy in the form of light. Based on the wavelength of the light, which determines its color, we can figure out how much energy was released. And that gives us the approximate location of where that electron was when it released that energy. So this picture, based on the release of energy from atoms, gives us the location of where atoms were at some point in the past. Okay? Like I said, these are not electrons, these are old locations of electrons. Okay? And Joe, like you noticed, right, what do we see in there? There are certain places where it's darker than other places. That means what? Okay? Because why? The fact that it's darker in more places than other places, what does that tell you? It's been there more times, than other places, right? And if it's been in a certain location more often in the past, what do we kind of do? We can predict that it will be there more often in the future. Okay? Go ahead. So here, these lights are a mixture of gases. So it's a hodgepodge of a whole bunch of different types of energy and light that's being given off. But if we can isolate a single gas, what we find is that it doesn't give off a big hodgepodge of light. It gives off a very specific wavelength or combination of wavelengths. So if you look at one specific one, it gives off a certain amount of, hold on one second, let me do this. A mixture, like, so that's a fancy word for a mixture, so. Yeah, it's very, very. All right, so let's go here, and let's look at the emission spectrum for hydrogen. Okay. It's just not very. Okay. All right. So when we analyze the light that comes out of hydrogen, we can get a tube, just like a bulb like this. Usually it's not as wide as that. It's much thinner, not as big of a radius. But we do the same thing. We hook it up to an electricity source, turn on the electricity, and the tube glows. It gives off light. In hydrogen, it gives off only some very specific wavelengths of light. So you guys can see there's a pretty big, bright red one right here, right? Then a couple bright blue ones, and then there's sort of some dim purple ones. Okay? Is that, yes, are you guys seeing that? Yeah? What? Okay. This one over here? Those are purple. Those are purplish, all right? So those lines represent certain jumps of electrons, or in this case actually falls for electrons. Because if it falls from like here to here, it gives off a certain amount of energy. But if it falls from here to here, it gives off more energy. So red, what did we say about the energy that red light carries? Is it a lot of energy or a little bit of energy? It's the least, right? At least in the visible spectrum, right? There's other waves out there. So this is not a very big fall, okay? But these ones up here are from higher levels back down to lower levels, okay? Joe, go ahead. No. It would look like a single color. It looks more reddish because that's like the brightest one. There's a little bit of mixed in there. This is what happens when we run the light from a hydrogen bulb through a prism. This is what happens. Okay? If we run this light through a prism, we get all the colors of light because it's all mixed together, right? If we run the light from a hydrogen bulb through a prism, it shows up as these very specific lines. Because not all the colors of light are in there. There's only some very specific colors. Okay? Jason, go ahead.
So you said when you add energy, the electron goes to like a higher shell.
Yeah.
Can only go one shell higher.
Nope. Depends on how much energy it gains.
Yeah, exactly. So if you pour more energy, why doesn't it change color instead of get brighter?
Well, so these different lines represent the different like falls that it can take. Some of them are brighter than others because they happen more often.
Yeah, well, okay, let's say there's white light right here.
Yeah.
So if you add more energy, it gets brighter, right? But it's like some, or no. Okay, let's say you have a red light.
Okay.
So if you pour more energy into it, it should turn like orange.
What we find is that depending on the gas that's in there or the material that's in there, while all jumps and falls are possible, some of them happen more often than others. Does that make sense? And so I see what you're saying. Yeah, like you're saying, oh, well, if I give it more energy, it should just go to a higher level. Sometimes it doesn't necessarily go to a higher level. It just goes to that level more often, like a lower level, but it Yeah, maybe quicker, like up and down, up and down. It gives very specific lines. And hydrogen, this is what it looks like. Okay?
So if it gives enough energy, it just, like, get brighter and brighter.
No, yeah, it would just get, like, these lines would just get brighter because it's happening more often.
So you can only jump for a certain,
There's specific jumps that they make.
so that's that. They can't do more different than this.
Well, each one of these represents a specific jump.
Yeah.
Okay? And so we'll find in a second, right? How high does it want to jump? That's a stupid question. My bad. Bad, poorly worded question. Is it more likely to jump to a higher level? Is it more likely to jump to level 2 or to level 7? Level 2, I know what you're saying, it depends on what energy, but what's different about level 2 versus level 7? It's closer, meaning that the electrons don't have as much what? What kind of energy specifically? Potential energy, right? So that jump from level 1 to level 2 is more likely than the jump from level 1 to level 7. Does that make sense? And if an electron jumps from level 2 and falls back down to level 1, immediately one of the ones that needs to jump up, it will jump up to 2 instead of all the way up to 7. Does that make sense? It tries.
So that means that no electron at 2 level 2 will eventually jump up to level 7.
If level 2 is full, then it'll try and jump up like to the next level. Does that make sense?
Yeah.
Okay. I know what you're saying. I get what you're saying. If we add more electricity, we should have all these electrons jumping up to really, really
go
high. Yeah.
higher or go faster.
Right.
But most likely just goes faster. Why doesn't it go like higher? Like, no, see, like this.
No, I know what you're saying. I'm trying to.
It's okay, just continue the lesson first.
Okay,
I'm
so-
last time.
All right. This is what hydrogen's emission spectrum looks like. Okay. So let's do this. No, let's go back here. Let's go this one. Of course, the picture that I want isn't anywhere. Oh, there it is. All right. So, here's hydrogen, here's neon, here's iron. Okay? There's the periodic table.
26, we got it.
Here's hydrogen, here's neon, and neon is what? 10, so it has how many electrons? 10. Iron is 26, so it has 26. Look at how many lines iron has.
Look up the last one. I don't know how to say it.
It doesn't. I don't think it exists long enough to actually get an emission spectrum, right? So when we add more electrons, we have more lines. We have more possible jumps. Some of them are brighter than other ones, and that's where we get this idea of, okay, these are where these electrons are located more often than others. Okay? Good? Let's see if we have it. There it is. See it? So, lots, right? Lots of electrons jumping, right? Lots of different transitions that it can make. Uranium's 92. So, it's the highest, it's the biggest atom that occurs naturally in the universe.
Like all the ones without being.
Those are all like stuff we made in a laboratory.
You know all the.
No, like not off the top of my head. So.
So how do you say the name of the last one?
Well, that one's actually kind of like it's like unoctinum, something like that. It's yeah, it's Latin for 118. ish, you know. So yeah, well, that's what it gets. It gets like sort of that name when people like discover it, and then they're like, hey, you know, and then you like if you discover it, you get to like propose a name to the international board of chemistry, basically, and then they kind of give you the thumbs up or the thumbs down, you know. Like,
What if you don't? What if they give you a thumbs down?
what?
If they give you a thumbs down, how do they come?
I don't know. Maybe they let somebody else. Maybe they put an ad in the paper or something. You know, like, hey, name this element. So or like, did you guys see that the zoo had a baby rhinoceros that was born recently? So, baby rhinoceros was born at the Cleveland Zoo like in the last week or so.
I hate you because I think
Most of those animals would die if they put them out in the wild because like they were all born in captivity, but for the most part, so they don't know how to like live in the wild. So. But long story short, the zoo is holding an online poll where you can vote on what they should name the new baby rhinoceros, but you have to make a donation like to the World Wildlife Fund to do it, like, which is, I guess, it's kind of cool. Yeah, like, you know, like we'll let you vote if you give $1 to animal conservation. So I wanted to call it I thought we should call Riney the rhinoceros, but it's a girl. So, but Riney wasn't one of the names that they
what were they?
I don't know. All right, up on the board are pictures of two orbitals. Okay. Yesterday we introduced the concept of an orbital. Right. An orbital is a place where the high probability of finding electrons. So an orbital is a space with a high probability of finding electrons. Meaning on this picture, where the dots are real close together, that's an orbital. Okay? What we're going to do over the next couple days is we're going to see that orbitals come in lots of different shapes and lots of different sizes. What we're going to do is we are going to classify them. We are going to distinguish all of the orbitals from each other. Okay? So, I don't want you to freak out when I show you the next picture. Okay? But over the next couple days, this is what we're going to draw. Okay?
Wait, do we get like those cool?
That's so easy.
So, okay. This is where we're headed. Right? All of the shapes that are on this picture, these are all separate orbitals. They have different shapes, they have different sizes, but they're all places where electrons could exist around the nucleus. Some have higher probabilities than others, but we're going to come up with a way to distinguish them all from each other. Okay? There are orbitals inside of orbitals, because we're like dealing in 3 dimensions here, you know? So this picture also comes out this way. So it's kind of like, so Shane, if you want to think about it, it's like, you know those like little Russian stacking dolls where there's like little one and then goes, that's kind of what we're dealing with here, is that sort of, you have this and then you have this surrounding it and this surrounding it and that kind of stuff, okay? All right, we're not going to start here. We're going to build to this, okay? So here's what we're going to do. I'm going to try something a little different this year, something different than I've done in the past. We're going to draw the picture first, and then we're going to put names and definitions on the picture. Okay? So a lot of times in the past, I've kind of given the definitions first and then drawn the picture. I think I'm going to try it backwards this year and see how that goes. Okay? All right. On the back of the outline that I gave you today, you guys have a couple different sets of X, Y, Z axes. Okay? This is a 3-dimensional picture, so we need to draw it somewhat represent the 3-dimensional nature of it. Obviously, that's hard on a flat piece of paper. The horizontal solid line represents the x-axis. The vertical solid line represents the y-axis. The diagonal dotted line represents the z-axis. Are we good with the idea of the z-axis? Right? If x is horizontal and y is vertical, z is front to back. Right? So the z-axis in real life is going to come out of the paper towards you and go into the paper behind it.
Like this.
This is X, this is Y, this is Z. Okay? They're all at 90 degrees to each other, right? Because an X and the X's have to be at 90 degrees to each other. Okay? So this is what we're drawing here, right? Sometimes we're going to have to draw stuff on the Z-axis, but we're going to have to do our best in 2 dimensions. Okay? Got that? All right. Here's my intention with the XYZ axis that I drew on the back of your notes. The big one up at the top is going to be your version of the big picture that I showed you before. But that's going to be complex by the end of it. There's going to be a lot of drawing over and stuff like that. So the ones on the bottom are intended for you to show a little bit more detail about certain parts of that drawing so that you don't have to try and get it all together while it's all done. Okay? All right. So let's start at the beginning. Where is the most likely place for us to find electrons? Around the nucleus, right? Why?
Because that's what
Okay. That's where the what? That's where the least energy is, right? Also, if we talk about it from like an attraction standpoint, what charge does the nucleus have? Positive. What charge do electrons have? Negative, right? So we are very likely to find electrons close to the nucleus. Oh, hopefully you got this, but just in case, right? The origin of this graph is the nucleus, okay? That's where the nucleus is in the origin, okay? Now, just like on your bullseye lab, the small ring surrounding the center, for most of you, didn't have very many marble hits in it, right? Why? More so, there's actually another reason. It's small, right? While electrons want to be very close to the nucleus, if too many of them start getting there, what starts happening? It gets crowded, right? And if we get too many electrons near each other, what do they start doing? They start repelling each other, right? So the first spot on the first orbital that we run into is very close to the nucleus, but it's not very big, okay? And so here is my first orbital on my picture, all right? So, hold on a second before you draw, okay? First, I would recommend drawing this pretty small, surrounding the origin of the graph on the top, okay? A small circle. Is it actually a circle? It's actually a sphere, right? So we're going to draw a small circle surrounding the origin of the graph on the top. Okay? Anything that distinguishes color would be fine. Like I said, there's going to be, especially on the top graph, we're going to draw over our drawing a lot, and that's why the bottom graphs are going to be there to sort of allow you to show a little more detail. Just go ahead. Say again? This one I would start on the big one, okay? Because there's really, you'll see here in a second that there's not much after this one. All right, this is our first orbital, okay? All right, ready for the second orbital? Okay, don't draw anything yet. Let's talk, then you can draw. Okay, so, hold on, before we draw, hold on. That's red. You'll see up, Joe. You'll see up here. Mine have like a solid outer, and then they're kind of shaded in the middle, so you can see what's underneath them. Okay, which is part of our discussion here, right?
We do that?
Hold on a second. Stop. Let's talk first. Okay? All right. So, what do you notice about this orbital compared to the previous orbital? Compare and contrast. Okay, it is bigger, but they're both spherical. However, what has to be true about that red sphere? Again? Doesn't necessarily include the smaller one, but what does it do? It surrounds the smaller one, meaning that the red one is actually what? It's hollow. Okay? It surrounds the yellow one, but it's hollow, like an egg, right? But it's hollow because the yellow one exists inside of it, okay? Similar in shape, a little bit bigger, right? but hollow. What can you tell me about electrons in this orbital, the red sphere, red hollow sphere, versus the yellow sphere? Tell me about the electrons in that orbital. They have more energy, right? Why? Farther away from the nucleus, right? So the lowest energy electrons are going to exist in the yellow sphere. The next lowest energy electrons are going to exist in the red sphere. Okay? So here's what I would recommend. All right, I would draw your next color sphere surrounding your original color sphere on your big drawing up at the top. Okay? And then, on one of your small XYZ axes down at the bottom, using the same color as the second color, go ahead and draw that sphere again on one of the smaller ones down at the bottom. So your orange circle, E, draw it again down on the one. Yeah, just the orange circle. You don't necessarily have to make it as big as you made that one, because we're going to show some variation within a couple of different, and on my drawing, red orbitals. Okay? Joe, go ahead. I don't, but I can get you another one.
It's not
Did you bleed through the paper?
well, not,
No,
he
I
is,
did,
it's not
but-
perfect. No, it's not.
So again?
It's just that.
Like fill in.
Oh, Phil, if you want to show that, like I can do this on the computer, obviously, like I can make it a little shaded. If you want to show that, yeah, it's a little shaded, like you can do that. That might be a good idea, just to represent the fact that we're surrounding that first orbital. Okay. All right, good there so far. Okay. All right, you know what? Why don't we call it a day, and we'll add the next part. We'll add the next couple tomorrow. Okay. All right, if you would please make sure that our stuff ends up back in the container, not just all over the floor, next to the container, please. Those pencils will be out for the next couple days, so we will use them over the next couple of days. Okay? Good start today, everybody. We'll build on this tomorrow.